Welcome back. Today we're going to talk a little bit about simplicity, and the story starts with these two gentlemen, Pierre Duhem, a French physicist, and William Quine, a American philosopher. Duhem, his story is that he was a physicist and he thought, I don't have a whole lot to do. I'm going to go back and I'm going to check Newton's results, get his data, get his calculations, and I'm going to work through the whole thing. And realizes that actually that's problematic. Um, when you take Newton's data and the assumptions he made based on missing data, because he didn't have tons of it, right? So we have astrological, or I guess astronomical observations as far back as Babylonian time, but we don't have every day, every night kind of where when Mars appeared. We have occasional glimpses at historical records. And so Newton used uh, the theories of planetary motion available to him to fill in the missing ones. And but that's problematic because, in fact, what Newton was coming up with was something that would supersede that. Um, in fact, there's internal contradictions between what Newton predicts and the data he himself used. And so Newton is kind of wrong about how he got to his conclusion. In fact, he probably kind of jumped ahead to it and then found the data that he needed to support it dangerously close, it looks like, to just straight up cherry picking or being a Texas sharpshooter. Duhem concludes that Newton used hidden assumptions, ignored contradicting information, and yet was basically right. Right? Newton, in his laws of motion, pretty darn good. Up until we start going past the speed of light, he's pretty solid. But this starts to look like science maybe isn't as rational as we thought, because Newton comes up with this incredibly scientific, incredibly brilliant theory, but the data was kind of wonky, and so what's up with that? And Duhem says, look, we're wrong about how science works here, in that every researcher, everyone's sort of using data as a group, not individuals. So he calls them theoretical groups, and this is how he proposes physicists should proceed. The American philosopher Quine realizes that this is probably not just physics that has this problem. And so he writes this book, Two Dogmas of Empiricism, in 1953, that led one of my professors to call Quine the Antichrist, for kind of tearing apart our, our preconceptions about human rationality. Uh, the year I finally want to get fired by the university, I'm going to use this book as my text for critical thinking, and we're not going to get bogged down in categorical logic. We're going to go right to the end. But in the meantime, we'll work through this. So, Quine's slogan is all hypotheses are tested against the background of all relevant assumptions. And the claim is it's impossible to test a theory in isolation. We're always making assumptions, even when we design our experiments. We're making assumptions. For instance, in the vaccines, we're making assumptions that the people in the control group are similar enough to the people in the vaccination group to show statistical results. Suppose that, unbeknownst to us, the people in the control group, went to some effort to try to get COVID, and the people that they were vaccinated, locked themselves down. Well, then those results would be meaningless, right? So we're in every experiment, you are testing everything relevant, and even things like the logic of your experiment, the meanings of the words by which you describe your experiment, and so on. All of that is a big bundle, and then when you run your experiment, you're testing everything all at once. So, and as an example of this, Newton's law of gravity could be confirmed by observing planetary motion. When you want a good test of Newton's law of gravity, you want big, heavy things attracting each other. It's not going to work with two thumbs trying to move together. And so, if you figure out the math, which you'll figure out the math by figuring out the motion and vice versa, right? It's all kind of a great big question begging thing. And the positions, and then when you get that all rolling, you realize, well, actually this planet Neptune isn't showing up where we would have predicted. We're predicting Neptune's going to be right there in the sky, and then lo and behold, it's just a little bit over. Oh, Tiger, for crying out loud, Tiger, just relax. It's okay, Newton's not wrong. And so at that point, you could say, well, obviously the laws of gravitation proposed by Newton are wrong, because his prediction that Neptune's going to be right there didn't happen. Instead, people go, well, maybe we're missing something, right? And sure enough, turns out that if you realize that there's an eighth and sort of a ninth planet, and you get those things into the model, oh yeah, well that explains exactly why Neptune is there. And so even though you have that disconfirming case, we did not get our expected observation, we don't throw the theory away. Instead, we kind of check all the other assumptions to see where we went wrong. So remember these two arguments, right? Where this one is the fallacy. This is the valid one, right? If our theory is true, then we get the expected observation. We don't get the expected observation, therefore our theory is not true. That's what should have happened in the Neptune case. We didn't see Neptune where it should have been. But rather than that, what scientists actually did was they said, look, if our theory and our auxiliary hypotheses, that's all the other background assumptions, are true together, then we should get our observation. We don't get our observation, therefore either our theory or our auxiliary hypothesis is false. Just relax. I know you're interested. And if you want to satisfy yourself that that's a valid argument, a lot of people have questions about how we get from the, sorry, I didn't, this should be ampersand instead of a dot. I didn't make that correction, my mistake. How we go from the and to the or. Well, that's why I showed you De Morgan's theorem a little while ago. And so in fact, and if you don't believe me, do a truth table. I beg you. In fact, that would be a fantastic exam question to perhaps just recognize the correct truth table that demonstrates the validity of this argument. So, that's a valid argument, okay? And so the upshot of it is, whenever you have a theory that appears to have been falsified, you can always sort of do a little bit more digging and find out if you missed something. And is there some auxiliary hypothesis that's wrong? And so falsifications, Popper's falsification actually even continues to kind of go down in importance because you realize, well, actually all we know is that something's false, not necessarily our theory. Popper kind of anticipates that, and he says those theories which rely on the fewest auxiliary hypotheses and make the boldest predictions, and they're therefore more easily falsified, are the best theories. Any theory can be saved, at least in theory, by adding other assumptions, other hypotheses. So, and we call these ad hoc hypotheses. And that's a fancy Latin word. Ad hoc means for this, or perhaps even specifically for this. So, and those words are used in common English, typically either for in legal descriptions of something like a committee, either parliamentary committee or a board committee. When you have an ad hoc committee, you say, well, this is a committee that has one specific job. Once that job's done, they're out of here. An ad hoc hypothesis is adding something to a theory just to kind of make it all work. We also use ad hoc in ordinary language to mean kind of made up. And so if someone said Manitoba's COVID plan seems ad hoc rather than the result of careful planning, right? So that ad hoc is used somewhat pejoratively there. So as an example of an ad hoc theory, and I don't want to get, maybe this is a bad example because it's controversial, but the theory of creationism, that over a relatively short period of time, a single supernatural being made the earth appear as it is. And, this is a theory that for a time, a large portion of the world's population accepted. But we've come to understand that there's quite a bit of evidence against this, right? When we start digging up dinosaur bones in Alberta, people go, oh boy, these are a lot older than 6,000 years. What's going on here? And now, did everyone say, forget it, bad theory? No, there's lots of ways you can continue to believe that, right? So, one creationist that I'm mostly amused by, a guy named Dwayne Dish, says God buried the dinosaur bones just to kind of give us a little bit of a puzzle, to exercise our intellect. He also sort of has this theory that, actually, there's all this stuff buried in the ground is evidence of Noah's flood, and so that's confirmation. And he's got wonderful things to say about why the dinosaur bones are buried before say the human bones. It's fascinating. So at the same time, here's a different story about ad hoc hypotheses. Einstein, who's no slouch in the brains department, he thought the universe was stationary or constant. And but when he started doing his work, realized that his own theory predicted that there wasn't enough mass in the universe to continue in a stable form, and it would ultimately collapse. And Einstein says, well, I can't have that. And so he kind of pulls out of his butt what he calls the cosmological constant, which is basically, I'm going to multiply everything by 1.4, and then we're fine. And in his middle years, tended to call this his greatest blunder, essentially to say, I'm going to add another hypothesis to my theory in order to give me the result I want. Now, what's interesting is our current best theories actually have him only off on this constant by a couple hundredths of a percent. So, what was his greatest blunder, actually turned out to be something that has stood the test of time. So, just because something's ad hoc doesn't mean it's wrong. That's the gist of those two stories. So when Popper says, yeah, I prefer the simpler theory, we got to understand that in some way. We can't just say, forget it. If it's ad hoc, we have to reject it. And so the rule of thumb we're going to rely on here is Occam's razor, which is named for a guy named William of Occam. This is him sitting there counting on his fingers, trying to keep that number low. And his slogan, if you translate it from Latin directly, it's don't multiply entities beyond necessity, or use only what you need. Conceptually use, right? Now, his name gets spelt a bunch of different ways because he's William of, and the way that town has spelt its name has changed as different marauding hordes have come through there. He was a student at Oxford University, but never actually graduated, even though he later taught there. And so his nickname as a monk was the worthy beginner because he never graduated, which, I guess is maybe at this point in the term some consolation to those of us who are discouraged about how things are working out. You could end up with a cool nickname. And the gist of Occam's razor here is that we should prefer the explanation with the fewest possible numbers of causes, factors, or variables. So now, what the heck? Tiger, you're always such a nuisance. Here we go. Just relax, okay? So the ad hoc hypothesis will have this effect of making theories complex, but this is not some sort of logical law or rule here. This is going to be okay, you just need to stop. Yeah, no, away you go. Go on. This is going to be a rule of thumb, not some sort of law of logic, right? This is not going to be like, rule 3 in syllogisms where if it does this, then it's invalid. This is going to be like judgment for informal fallacies, like, that's a little bit sketchy. Okay, so when we're applying Occam's razor, which has that cool name, which makes it sound like you're slicing stuff and really being decisive, in fact, it's a judgment call when you're asking what's simpler. But there are a couple things I can say about that. So here's two theories for why the world appears as it is. One theory, especially the biological world. All species on Earth are descended from a few common ancestors and have evolved by genetic mutation to fit particular ecological niche according to or by survival of the fittest. And to really make sense of that, you need gene theory, continental drift. You're gonna have to understand all sorts of crazy stuff. Or theory 2, God did it. Snap of the finger. Now, which of those two is simpler? Now, given that we can wrap our heads around this one pretty much right now, whether is this one to fully understand as a lifetime of study in biology and maybe other disciplines in the sciences as well, seems like we like this one as simple. So, but let me caution you about that. When we talk about simplicity here, we're not talking about which is easier to understand. We're asking which one has fewer entities, causal factors, things in your theory, right? So when we compare this one to this one, remember that this theory is explaining all the species on Earth just the same way, but also has God, which this one doesn't have, right? So this has one more thing than this one does. And so strictly speaking, just on an Occam's razor criteria, this is simpler than this one, even though this is way harder to understand. So that's what I'll say about simplicity. You want to see how many, and let's go back to those fewest possible number of causes, factors, or variables. That's how you count simplicity. So that is where our textbook gets to with these, what we call the virtues of science. And these are not logic things, but we've done simplicity, we've done testability so far. And in the last couple lectures, we'll pick up on the rest of those criterion. And so that's where we'll leave it for today.